Good morning, guys. Start with green check marks, please. And we'll get going here in a second. Thank you. If you guys have any questions from section 5.1, we did acids and bases last day. If you had any sectional questions that you wanted me to go through from there, if you just want to fire those into chat, I could go through those. And if nobody has any questions on that stuff specifically, then I will... All of them 13? Okay, good. There's a few questions there. All right, and I can go on to 5.2 and 5.3. They're both really, really short sections with a little bit of information in them, but nothing too terrible. So let's have a look at 5.1. So we went through the acid names, and be pretty good. Eric's asking about number 18, which doesn't appear to be a question that I have, unless you're talking about something out of the next section. 13, sorry, 13. I don't know why I said 18. It's not the right section. Here we go. 9, 10, 11, 12, 13. Okay, so the ions that these things release. So in the notes, the acids and bases are acids and bases. So acids are acids because they have that hydrogen in them, and then bases are bases because they have hydroxide. So this is the page production of ions. So right from the notes, acids release hydrogen ions because that's what defines an acid. So I mentioned last day, anytime you put an ionic compound, sodium chloride, whatever, any ionic compound, acids and bases included, although they're not ionic. I suppose they are ionic. They are ionic, yeah. You put them in water, they won't stay as a sodium chloride. The sodium will float free and the chlorine will float free, and you get these ions that are produced. So that's the same for acids and bases. When you have an acid, all acids will have H in them. That's what makes an acid an acid. When it is free in water, you dissolve an acid in water, the H will float around, and then the whatever else was with the H will float around as well. Same with bases. The bases will have the hydroxide kind of break apart from whatever it was combined with. So acids release hydrogen, H+, and bases release hydroxide, OH-. That's right. From there, so hopefully that answers your question there, Eric. Was there anything other than that? Oh boy. Appears as if my pen is not working, which is just splendid. Maybe I can write with this. Hydrogen. This is not the best method of doing things, but it'll work, hey? Beautiful. Now, for the record, that wasn't with the nice touchpad, that was with the little red scrolly button in the middle. Pen's definitely decided to not be working, which could make things a little bit interesting for the rest of class. So, any other questions from that section? Acids and bases. Anything specific? Or figure you got her under control? All of them? Kyla, was there anything that was more difficult perhaps than some of the other questions? Mm-hmm. 15. So fill in the table below with important information. Do not simply copy everything from the website. All right, so just kind of summarizing acids and bases, color and litmus, reaction with metals, pH. So this was just exactly the same as the chart. I think it's actually in the learning guide, if I'm not mistaken. Let's see if it's there. Up above. Taste, touch, indicators. So it's just information right out of this table here. Acids taste sour, bases are bitter. Acids burn your skin. Bases feel very slippery when you get them on your skin. Doesn't matter what litmus paper you use, acids will be red, bases will be blue. Acids react with metals, bases don't. pH, acids less than 7, bases greater than 7, or acids from 0 to 7, and bases are from 7 to 14. Out of the notes there, out of the learning guide. Anything else? Go through, point you in the right direction. Why is it not possible to have a solution that's both highly acidic and highly basic at the same time? I'm just going to go back to a little picture out of the notes here. There's a little chart right here. So when we have an acid and a base and we mix them in water, say we mix some acid with some base, when you mix the acid in, you get the hydrogen kind of floats off by itself. When you mix the base in, the hydroxide, the OH floats off by themselves. So when you get right in the middle of this little diagram here, when you get equal numbers of H and OH, so that's everything that's neutral in the middle of our little chart here, what happens is you get an H and an OH, and the H and OH, they stick together. And what is HOH? Well, that's just water, it's H2O. So if you have the exact same number of OHs as Hs, they all stick together and you have just perfect water. Nothing else there. Completely neutral, pH of 7. If you have a couple extra OHs, then all of a sudden you're kind of, on this side of the scale, and you have a couple OHs and you're a little bit on the base side. If you add a couple more acids, the H and the OH combine together to give you water, and then you start moving back towards the H side. So you get a little bit extra H's floating around. Now whatever you're dealing with is acidic. And you can get more and more H's, and it gets further and further acidic until you get down close to a 0 with just lots of hydrogen ions there. Or you could do the opposite. You could move down to the OH side of things if you have a bunch of OHs or bases present. So right in the middle is neutral, and in science we call that a neutralization. So when you have equal amounts of acid and base, they mix together and just give you water. So you can never have acids and bases at the same time, because if you have, let's say you have 5 acids and 7 bases. Well, the 5 acids and the 5 bases will combine together, and then you'll have the kind of 2 bases left over. So you can't have both at the same time, because as soon as you do, they combine to just produce water. And that is what is in the very middle, are neutral substances. It's good, hopefully. Anything else? Didn't understand? Want me to go through again? Questions about? No. All right. Yes, possibly. We can go into the salts and organics. It is not a lot of material. There's some interesting stuff in it. If you guys have more questions that you run into with that 5.1 stuff, we can go through it at the end. We'll get this out of the way. So salts and organic compounds. This is section 5.2 and 5.3. They're not very big, so we just put them together. So salts, organic compounds, we've already talked about salts, and organic compounds is something new and confusing for students the first time they encounter them, so perhaps you've seen them before. So anytime you have a metal and a nonmetal, an ionic compound, those things combine together, they are a classification of compounds called salts. So if you start with an H, you're an acid. If you end with an OH, you're a base. So those are categories. You can have HCl, you can have HS, H2SO4. Those are all acids. So that's a category of compounds. Starts with H. If you end with OH, those are your hydroxides. You can have sodium hydroxide, magnesium hydroxide, calcium hydroxide, iron hydroxide. All of these things are bases. So that's another category. And then you have another category called salts. And salts are your metal, nonmetal, ionic compounds. So the reason this is kind of confusing is because you have this preconceived definition of a salt that is the stuff that sits on your kitchen table that you put on your food to make it salty. Well, sodium chloride or table salt is just one kind of salt. There are many, many hundreds of salts. Salts is a classification of compounds. The most common, the one that we use, is table salt, NaCl. So why is it so plentiful? Well, that's kind of the main salt in seawater. So, if you go back 1,000 years or more than 1,000 years, salt was a major commodity. People went to the oceans and, mined salt in the salt flats and took it back to their village and traded it as currency and stuff like that. It's been a major part of sort of human civilization for a long time. So that's why salt is kind of important. Salt is just a metal and a nonmetal combined together in an ionic compound. So that's what salt is. What do we use salts for? We use salts in things like batteries. So we have all this new fancy battery technology has lithium batteries. So lithium ion batteries are lithium combined with usually something else like oxygen or something like that, and that produces or holds a charge, so you can give it a charge. So you have lithium batteries. You probably may have heard of NiCad batteries, nickel cadmium batteries. Again, those are nickel and cadmium combined with nonmetals to produce salts. Those are batteries. Explosives use salts and fertilizers, and fertilizers and explosives are essentially the same thing. You can make explosives out of fertilizer. Multivitamins have salts that your body needs. So if you need something like iron in your body, if you're iron deficient, you don't just go grab a chunk of metal and start chewing on it. Your body can't absorb that solid iron. So what do? Well, they combine the iron with something, and your body can break the iron off of whatever it was combined with and utilize it that way. So a lot of multivitamins have many, many different salts in them to provide your body nutrients, those micronutrients that you don't need a lot of. And that means that majority of your living cells in your body have salts in them. Now, this is, we've done neutralization reactions already. So acid base produces salt and water. So you've seen that. In Unit 6, we covered the neutralization stuff. The other two are metal oxides in water and non-metal oxides in water. And there's always one question on a test in regards to this stuff. I think it's just kind of a waste, but then again, it's just my opinion. So why is it important to know how a metal oxide reacts with water? Probably, or non-metal oxide more specifically. When I was growing up, when I was in Science 10, there was a big problem with acid rain. So we were producing lots of non-metal oxides by burning coal and stuff like that. It was going up into the atmosphere, it was combining with water, and then it would rain. And the rain would be acid rain. And acid rain was a really kind of a big thing when I was younger. It's not so big anymore. We have more sort of environmental protections in kind of North America and Europe. Other parts of the world, it is still a bit of an issue. So basically acid rain sounds like this terrible thing, like acids falling from the sky. Well, it wasn't like acid with a really, really high pH falling from the sky, but it was just slightly acidic, which was a big deal because when you have acids falling on, ancient buildings and things like that, or, murals or things that are carved out of stone, the acid just slowly eats away at it. So it's not like acid fell on a house and the house just dissolved and disappeared. That's not what acid rain is. It just kind of eats away at things slowly. It lowers the pHs of soil and makes the ground less fertile. So you end up with kind of stuff like that when you talk about acid rain. So metal oxide. Anytime you mix a metal and an oxygen, you get a metal oxide. Makes sense. Non-metal oxide is a non-metal and oxygen. That hopefully makes sense as well. Anytime you mix a metal oxide and water, you end up with a base. So you essentially the water breaks down and you get an OH from the water, and it combines with the metal and you get a base. The opposite's true for non-metal oxides. If you have a non-metal oxide, you mix it with some water, you end up with an acid, and then you get acid rain. So these are kind of two reactions that occur. Unfortunately, you just have to know what they look like. Hopefully you can recognize a metal oxide and a non-metal oxide. They're, again, kind of classifications of compounds. A metal and an oxygen is a metal oxide. A non-metal and an oxygen is a non-metal oxide. So anytime you have something like Na2O, that is a metal, sodium, and then oxygen, metal oxide. And then if you have something like S and O, or SO2, that's a non-metal, sulfur, non-metal, oxygen, oxide. It's probably not extremely important that you are able to predict what's going to happen, aside from the fact that you should know that a metal oxide and water produces a base, and a non-metal oxide and water produces an acid. There's probably some fancy mnemonic you could use to remember the difference between the two. Like I said at the beginning, rarely do these questions come up. Maybe you'll see one. So it's not a really, really big part of the course. The important thing here is that anytime an acid mixes with a metal, you're going to produce hydrogen gas. So how would you know that that was going to happen? Well, all acids have hydrogen in them. So if you are mixing an acid with hydrogen and a metal, you're going to produce something. Every time, it's always going to produce hydrogen because there's an H associated with that acid. So when you want to remember how these sort of reactions occur, you have an acid with that H, because that's what defines an acid. You mix it with a metal, and then hydrogen gas will be produced. It doesn't necessarily matter what the metal is. It's just a single replacement reaction, essentially. So you take any acid, HCl, HBr, H2SO4, whatever, you mix it with a metal, aluminum, iron, copper, gold, doesn't matter. You're going to get the acid's going to eat away at the metal, and hydrogen gas will be produced. Acids and carbonates is a similar sort of reaction, and carbonates are important because they neutralize acids. So we don't always have to use a base to neutralize acids. We can use carbonates. And sulfuric acid, calcium carbonate, produces calcium carbonate, water, and carbon dioxide. Again, you don't have to memorize this whole reaction, but you should know that when you mix an acid and a carbonate, it neutralizes it. Or if you mix an acid and a metal, hydrogen gas is produced. So essentially this whole unit 5.2 and 3 is just looking at sort of special types of reactions. We've classified our equations already in Unit 6. Now we have some special reactions. All right, I'll just leave it there for a second. Did anybody have any questions about any of those? I know it's kind of a lot of stuff. The reason I throw it all together and put the acids and bases and salts and the organics together is that they don't come up very often. They're not like a really big part of the course. All right, we'll move on to organics. Now, again, with like the idea of salts, students have this conception of salt as being that stuff on your table, but in reality, salt is a classification of compounds. Non-metal, metal together gives us a salt. When we talk about things that are organic, in your brain, what do you associate organic with? As soon as you hear the word organic, what kind of pops into your head? Healthy, for sure. When you go to the grocery store, you buy something that's organic. Generally speaking, yeah, farmer's market, people are like, come buy my organic produce, for sure. The irony here is that things that are organic that we eat means they're made without man-made chemicals and preservatives and things in that regard. The funny part about it is most of the chemicals that we're talking about are actually organic molecules. So when we say something's organic, it's not made with chemicals. There you go. So our organic compounds in science, in chemistry, have really nothing to do with the kind of idea that we have of organic in like a grocery store associated with produce, things like that. So organic compounds just contain carbon. If you have carbon in there, it's considered an organic compound. There's a few exceptions to the rule, but generally speaking, you get these long chains of carbon and you get an organic molecule. And one thing I always like to mention at this point is if you go on to university and you take any chemistry courses, first year university chemistry, the first half of the year, doesn't matter where you go to school, the first half of the year is inorganic chemistry. So the first half you'll study things like ionic compounds, metals, nonmetals, combining together. The second half of the year is organic chemistry. And organic chemistry is probably one of the most failed courses in university. It's tricky stuff. We don't get into it in any depth in grade 10 science. You just kind of say, has carbon in it? It's not one of the exceptions? Okay, it's organic. But when you get to university, you start having to name things like this. So we see this long chain of carbon with the black dots are carbons and the white dots are hydrogens. And you get a long chain like this, and you have to count how many there are. So there's 1, 2, 3, 4, 5, 6, 7, 8. You have 8 carbons, 8 black dots. And then you go to your prefixes, and you think, okay, 8. Okay, what is this? So this is 8. This is octene. And it's kind of like you come up with your prefixes. So CH, you have methane, CH4, and you add another carbon, it's ethane. And then you add another carbon, it's propane. And then you add another carbon, it's butane. So you've heard of these things, propane, butane. You add another carbon, methyl, ethyl, propyl, butyl, butane. You get things like octane and pentane and nonane and decane. And you have all these weird naming rules if it's just carbon and hydrogen. You add an oxygen on there, and now all of a sudden they become alcohols. You have methanol, ethanol, propanol, butanol. And then you, instead of having a long chain, you put it into a ring. Now it's cyclohexane, cyclopentane, cyclo, and you have all these other really weird naming rules. And then you get this kind of like little branch hanging off the side. So it'd be like 2-butyl cyclopentane, and you get into these amazingly complex naming patterns so you can name literally every organic molecule. And yeah, things are kind of really tricky. Costin, I'll jump to the learning guide in a second. There's only a few more slides here. So here is the sort of a summary of all of the organic compounds. So you have really basic organic compounds. 1 carbon, 4 hydrogens. The reason that organic compounds are carbon special is because it forms 4 bonds. So we are carbon-based life forms. All life on Earth is based around carbon. And the reason we're all carbon-based is because carbon's really good at forming really these bonds because it has these 4 valence electrons. It can combine with itself, it can combine with other things, all covalently. So there are, sorry, I'm just looking for the, exceptions. So anything that has carbon in it is considered organic, with the exception of CO. So I'm looking here in the chart, inorganic containing carbon. So if you have CO, that's carbon monoxide, it has carbon, not organic. CO2 has carbon, not organic, and CO3 has carbon, not organic. So if you have a CO, a CO2, or a CO3, so carbon monoxide, carbon dioxide, or carbonate, those big three contain carbon, but they aren't organic. Just about everything else is going to be an organic compound. The carbides are very rare, so I wouldn't worry about them too much. So, you know, everything you deal with in your everyday life has carbon in it. If you've eaten food, it had carbon. That's why we talked about the carbon cycle when we were in biology unit a long time ago. Food is carbon. These long carbon chains, these carbohydrates, our body breaks down into sugars, and we use that in all of our cells to provide us with energy. That's why we eat food, is to intake carbon, to replace the carbon in our body with carbon in food. So carbon's super important to life. Ethanol is a special type of alcohol, and ethanol, you know, we use alcohols for cleaning things. People consume alcohol, things like that. You have organic salts, you have caffeine, things like Tylenol, almost all pesticides, almost all pesticides are organic compounds. Our clothing, if I'm wearing cotton, organic compound. You know, cotton is a plant, essentially. The gas you put in your car, that's organic compound because it contains carbon. So all of these things. So it's important to not always associating organic compounds with kind of life. There's a lot of organic compounds like oil that aren't important to life, but you know, we use every day. So there you go. If you have carbon, it's an organic compound with the exception of CO, CO2, and CO3, and then a couple of carbides, but we will just ignore them. When you see a big C, like in chlorine, it's important to not confuse something like Cl with carbon. Remember, Cl is chlorine. It happens from time to time. Some students kind of get confused by it, but there you go. So I mentioned briefly methane, ethane, propane, butane, and pentane. And I have these little models. When you go to university, I'm just going to jump over here. When you go to university, you study organic compounds. So you get these little kits. Maybe you've seen these before. Maybe if you have an older brother or sister who's been in university. And these kits, you can make organic compounds out of them. So you get these little black guys, and these represent carbon. You'll see they have 4 kind of holes punched into the sides of them, and that's just representative of carbon. And then you get these little sticks that hang off the sides like that, and you can, you know, make carbon chains. So there's a 2 carbon chain, and 2 carbons is going to be ethane. And then you can add these little white guys, which represent hydrogen, and I can make this right here. This is what methane looks like. I have a carbon in the middle, the black dot, and then the 4 white dots around the outside all represent hydrogen. So that's what methane looks like, and this is what methane looks like. If I pull off a hydrogen, instead of that bond being with a hydrogen, I now bond it with another carbon. There we go. Now I have ethane. And I can just keep doing that. I can keep pulling off hydrogens and plugging on other carbons. And I end up with the next biggest carbon chain. So methane, ethane, and then propane. So if you've ever burned propane in your barbecue, or if you have a propane truck or car, some trucks burn propane, that's what you're burning. So when you hear all of this, if you ever watch the news, recently it's been in the news a lot. Christy Clark on the news talking about LNG, liquid natural gas. So LNG is kind of combinations of propane and other sort of organic molecules. And the reason these are really kind of good for the environment, or good compared to bigger chains like octane and things like that, is that there's fewer carbons in here. So I only have 3 carbons. So if I burn this in, let's say, a car, I burn my propane, it's going to break down these carbon bonds, and it's going to produce CO2 and some water. So there's not much waste when I break this down, because there's only 3 carbons here to begin with. But if I have something like octane is going to be an 8 carbon chain. So this is a 3 carbon chain. If I added another 5 carbons, so I had a bigger molecule, I'd probably run out of carbons here. But if I had a big octane molecule, and that's what I burn in my car if I'm burning gas, then that produces lots of waste. So there you go. So those are the basic carbon chains. That is 3 carbons, and then the rest are hydrogens. So that is an ethane, or propane, sorry. And there you go. So we'll just jump back to the chart here. So methane, CH4, that's 1 carbon, 4 white dots, kind of like what I just built here, the space filling model. If I take off a hydrogen and add another carbon, I get ethane. And then I get propane, which I just showed you, and then butane, and then pentane. And then I can just keep going. We start using our prefixes. So pentagon is 5. I can do I can do a hexane, which is 6. So penta, hexa, hepta, then octa, octane, nona, nonane, decane. So you have all of your prefixes, 2, 3, 4, 5, the ones we used before. So I can just kind of keep adding carbons, and I can make these chains literally hundreds and hundreds of carbons long, and they all have their own names. The majority of these things are flammable. You've heard of these before. Propane, you've obviously probably seen a barbecue burn propane once in your life. Butane, what's butane in? Does anybody recognize the word butane as coming from something? Nobody's ever heard the word butane before? Butane's the stuff that's in lighters. And butane's a bit special compared to something like propane, because butane is a liquid at room temperature, whereas propane's a gas at room temperature, but if you pressurize it, it turns liquid. And then pentane, it's in gasoline, and octane's the main component of gasoline. So if you ever go to the gas station, I just filled up before I came to work today. You look into the gas station, there's usually 3 or 4 different types of gas. You have 87, you have your 89, you have your 91, Chevron has 94. These are just ratings of octane. It's just telling you how much octane is in the gasoline. So an 87 is just a fancy formula they use to calculate how many octane molecules are kind of in that gas. If I have something like a 94, that just has more octane. It's going to burn a little bit cleaner, has less of the other stuff in it that we burn in our gasoline, a little more resistant to detonation. So if we look at this little picture here, this is an oil refinery. So this is how we get the different things that we like to burn. So we get crude oil, we dig it out of the ground, and then we refine it. Basically, we put it in this big tower, and we heat it up, get it real hot. And then at essentially different temperatures, you're going to be able to pull off different types of fuels. So this heavy oil at the very bottom, these really, really long carbon chains that produce massive amounts of fuel waste and whatnot. That's the dirtiest fuel that you can get. And I was reading something for a course I took last year, about this time actually, and it was talking about these big super tankers that ship things across the oceans. And I didn't believe it when I first heard it, so I had to go look it up online. You guys, I'd encourage you to do the same. But if you take a big super tanker that moves shipping containers back from like China to North America or all over the world, if you took the 16 biggest super tankers off the water, you just stop them from moving stuff at all, they produce, 16 biggest super tankers in the world produce the same amount of pollution as all of the cars combined. Millions and millions and millions of cars. 16 super tankers. It just kind of blew my mind. So the pollution that's produced by this bunker fuel, it's called, this really unrefined fuel, is just, it's really bad stuff that gets produced, and generally not good stuff. You get a little bit higher up the chain, you get into stuff like diesel fuel, which is less refined. You get a little bit higher, you get into kerosene, which is jet fuel essentially. And then a little bit more refined, you get into gasoline, which you use in your car, and then you go all the way to the top. At these kind of cooler temperatures, you get stuff like natural gas, which has stuff in it like propane and methane and all sorts of other stuff. So this is how all of the fuel gets refined. It's basically, you heat it up, you pull stuff off at different temperatures, and you get all these different types of fuel. All right, so those were hydrocarbons, hydrocarbon chains. You have CH4, methane, C2H6, ethane, C3H8, propane, butane, pentane. Let's just take a little mental snapshot of those things. Now we're going to move into something called alcohols. Now instead of having just CH4, if I put an oxygen onto the end of it, now all of a sudden I have methanol. So instead of methane, I had an oxygen group, I have methanol. Instead of ethane, I had an oxygen group, I have ethanol. Instead of, so methane, ethane, propane, I have isopropyl alcohol as propanol. I can have butanol, I can have pentanol, I can have decanol, I can have nonanol, and these are all your alcohols. So alcohol, like methanol or isopropyl alcohols like rubbing alcohol, methane or methanol you use as a solvent, so if you're like paint thinner and stuff like that. Ethanol, you've maybe heard of E85 ethanol fuel in cars. That's where they take this ethanol and put it into a car and burn it as fuel. It's efficient because you can take it from living things like corn. Ethanol is also the stuff that's in alcoholic beverages. So if you have ever seen a can of beer before, it says like 5% on the side of it. That means that 5% of that can has ethanol in it. And if you look at wine, wine's usually about 15% ethanol. And then you can get into the kind of harder drinks, refined alcohols like vodka and things like that, or 40% alcohol or 40% ethanol. And if we look at this picture of this oil refinery refining, different hydrocarbons off, so you have your methanes at the top, you have your really nasty stuff at the bottom. When you refine alcohols, it's the exact same process. It still works the exact same way. So these are your alcohols. And alcohol, again, we associate with what people consume or what we burn in cars, but alcohols are this general category of hydrocarbons. So I'll just jump back over here for a second. If I take my little ball and stick model here, and instead of having a carbon chain, if I put this red guy, which is an oxygen on here, now all of a sudden I've made methanol. So if I had hydrogen on the side, it's methane. That's what methane looks like. If I take off a hydrogen and add an oxygen, with another hydrogen on it, now that's methanol. And then if I lose another hydrogen and add a carbon, I like making ethanol because it Looks like a dog. Here we go. There's ethanol. Kind of looks like a dog a little bit. Woof, woof. If I turned it, it's not actually how it would form. Tell me that doesn't look like a dog. Somebody tell me it doesn't look like a dog. Anyways, that's what ethanol looks like. So that's the stuff that's in, thank you, Eric. That's the stuff that's in fuel. That's the stuff that's in alcoholic beverages. Looks like a dog, as far as I'm concerned. So there you go. These are your hydrocarbons. You add oxygen in there, they become alcohols. And again, alcohol isn't just the stuff you either drink or burn in your car. Alcohols are this broad category. As soon as you have a hydrocarbon chain and you have an alcohol, you just add an oxygen. That makes it an alcohol. When you get to isopropyl alcohol, so this bottom one, things look a little bit different here because this guy down at the bottom, because the oxygen's in the middle, so that's isopropyl. But the oxygen could also be at the end. If you move the red guy over to the end, now that's propanol. And this is where things get really tricky once you get into these bigger alcohol chains. It really depends on where you put the oxygen, the name changes. So isopropyl alcohol and propanol, although they have the same chemical formula, C3H8O, they are different things. Isopropyl alcohol you use in your house, propanol you don't. There you go. I find this stuff kind of interesting. Generally speaking, students don't. It's confusing. Do you have to memorize all of these things? No. You should be able to recognize something that has oxygen on it as a alcohol. If you have a carbon, hydrogen, oxygen compound, that's an alcohol. If you just have a carbon and hydrogen, that is a hydrocarbon. Hydro, hydrogen, carbon, carbon, hydrocarbon, hydrogen, carbon, that's it. You should know what methane is because it's really common, comes up a lot, CH4. And you can just see all the different structures here. Just pull off a hydrogen, add another carbon with a bunch of hydrogens on it, and you end up with these things. Does anybody eat like margarine at home instead of butter? People have margarine in their fridges. Any margarine fans out there? Yeah. So basically what margarine is these really long hydrocarbon chains. Margarine is just kind of usually made from hydrocarbons. Just straight margarine? Sure. Is there different types of margarine? I'm not a big margarine eater. Basically what happens with margarine is you have these long chains of hydrocarbons, and if you've ever heard the word saturated, that means that all of the carbons have hydrogens stuck on them. So that's a saturated or saturated fat. That's the idea here. Margarine is just these long hydrocarbon chains, and sometimes they'll pull off a few hydrogens to make it a little bit healthier. But that's kind of what you're eating when you're eating margarine, is these really long hydrocarbon chains that are kind of put together to make stuff we call food. I question whether it's food or not. So anyways, that's what kind of margarine is. You start seeing the word saturated and unsaturated. What's the word? Is there another word with margarine? I can't think of it. What's the margarine word? On the side of margarine containers, it's going to drive me crazy now. Let's look it up. Margarine. Let's find some pictures of margarine. Unsalted. Maybe not. Let's look at some Baecel. Can't believe it's not butter. Stuff's made from olive oil. Source of omega-3, source of no trans fats. Hydrogenated. That was the word I was trying to remember. I couldn't. So if you look at this one says it kind of here on the side, non-hydrogenated. So what does that mean? Well, hydrogenated is just hydrogen, right? Hydrogen, hydrog. So a hydrogenated margarine means that all of the, we can see it on the side. Thank you, Mr. Ross. Non-hydrogenated means that not all the carbons have all the hydrogens stuck on the sides. If you have something that's non-hydrogenated, you have a few hydrogens missing. If you have hydrogenated, that means that all of the carbons have hydrogens in all of the spots. There you go. Some everyday chemistry. Kaylin, what are you telling me here? Did you know that new ingredients used as substitutes for the original batch of margarine ingredients now unhealthy and cause buildup of unhealthy things? Yeah, there's always this kind of discussion surrounding margarine and whatnot, and I mean, it's basically what they're doing. You can see kind of behind my head here. This is a great picture of what margarine actually looks like. So you get these kind of these long chains, these lines, these up and down lines. These represent carbons. So every time you have a joint, you have a carbon. So that's a carbon, that's a carbon, that's a carbon, that's a carbon, that's a carbon. These two lines represents a double bond between carbons. So these are how you make margarines. You have these really long carbon chains with oxygens on one end. I could use my ball and stick model to make one of these if I really wanted. And basically, hydrogenated means that every time you have a carbon, one of these junctures, that all the hydrogens are hanging off on the side. If it's hydrogenated, you have full hydrogens. Non-hydrogenated means you have some missing. And generally speaking, non-hydrogenated is a little bit healthier. But yeah, Kaylin, we can look at some other organic molecules here. Not that I know what any of these are. But again, all of these little junctures where you have the intersections where these two lines meet, that's where carbon would be. And this is why organic chemistry gets so confusing, because you have to name these things, and they all have special common names, and then they have scientific names, and it's just, it's out there. But fascinating stuff. Got some good stuff happening here. Toluene. Yeah, I don't know what any of that is. Crazy. So this is just kind of shorthand for organic molecules. That's how to draw them. Instead of drawing like a carbon and then little lines everywhere with, like we have in the notes, like these guys here in this chart, this third column in the chart, instead of drawing methane like, it's loading. There we go. Instead of drawing methane like we've drawn it here, we just draw, one carbon. And then this ethane would just be two lines. So we just assume that everything that isn't carbon has a hydrogen attached to it. Propane would be 3 lines. Butane would be 4 lines. Pentane would be 5 lines. So just kind of those up and down lines like we saw. If I drew 5 lines, 1, 2, 3, 4, 5, that's shorthand for what pentane would look like. If I have an oxygen on one end, now all of a sudden it's pentanol. And you can just do all these crazy diagrams. Anyways, that's it for this section. Costin, you had a question. I wanted to get to that. I said I would. 5.2, 2, and 4. What type of compounds are salts? Are these the ones you're talking about there, Costin? Yeah, perfect. So salts are just ionic compounds. Ionic compounds and salts, they're generally the same. There's a few exceptions that are ionic but aren't salts. But anyways, generally speaking, we'll just assume that something is ionic. It's probably a salt, unless it's a metal oxide or non-metal oxide. And then number 4, what's the formula for table salt? Just NaCl. The stuff that you have sitting on your table at home, sodium chloride, NaCl. That's the common salt that we all consume. There's other salts that we eat too, but mainly, generally speaking, table salt is made of sodium chloride. You can get Himalayan salt and all these other things that have kind of trace other elements in them. Does anybody have Himalayan salt at home? I know my in-laws do. they have this huge Himalayan salt rock light thing, and it's just this kind of pink color, right? Himalayan salt's kind of pinkish. So basically Himalayan salt is mainly sodium chloride, but Himalayan salt has, trace elements, probably magnesium and stuff in it. If you go look at the side of the package, it might tell you exactly what's in there. So NaCl will be the main ingredient, and then you have some like magnesium chloride or these other kind of trace elements that your body needs to survive. And it's just another way. You could eat a multivitamin, or you could eat Himalayan salt on your food. It doesn't particularly matter how you get your nutrients. Those micronutrients, just got to get them in you. Stay healthy. So there you go. That's acids, bases, and salts and organics. Anything tricky in here? So you have acid and a base, going to produce a salt and water, metal oxide and water, non-metal oxide and water. So these are these, special types of reactions we just need to kind of remember, unfortunately. Remember a metal oxide and water is going to produce your base, and a non-metal oxide and water is going to produce an acid. Tricky questions. I will for sure go over those next day. Number 6. Have a go at it first, see if you can figure it out if you look at the notes and try to just kind of duplicate what's there. Non-metal oxides, the main cause of acid rain, just straight out of the notes. And then we went on to organics. And we talked about some hydrocarbons and alcohols. And what ion contains carbon but is inorganic? I wanted to write down the exceptions. I won't be able to write though because my pen doesn't work. Maybe it's working now. I never restart this computer because I'm always afraid of something happening to it, like what we have now. I wonder if I can just change tablet mode or something. Protected. Perfect. Yeah, I don't know how to get maybe I can insert a text box. Maybe? Insert file, table, space. What if I just start typing? Draw. No, don't want to draw. I'm giving up. Giving up. Next day, I'll go through the rest of this stuff. All right, so technically speaking, that kind of ends the chemistry unit. 4, 5, and 6 are the 3 big ones. The radioactivity unit that we do next, chapter 7, unit 7, it looks like chemistry, but it's technically not. We deal with some elements and protons and neutrons, kind of go back to the beginning of unit 4 again for a little bit. So I know we kind of spent a long time on unit 4, and then we kind of went through 5 and 6 real fast. So I do understand that. So for those of you who are just kind of, trying to finish up things, like I mentioned last day, just, if you're still plugging away at unit 4, just get in what you have and move on. Do 5 and 6, because if you're sitting scratching your head looking at unit 4 and then all of a sudden 5 and 6 have been added onto that, it's going to start to get difficult to make it through this stuff. So it's very important that a lot of you have submitted your work, and thank you for that. But if you're kind of falling behind here, just get it in, do the test, move on. We just can't spend any more time on it. So we only have 3 units left, and they're all fairly small. The radiation unit's only a couple lessons, and the physics stuff's only 4 lessons. So we're nearly done. We'll for sure have a week and a bit of review. And at this point, it's just a matter of getting the work done. So I apologize for not being able to use my pen and help you a lot further with the stuff here today, but I'll get it sorted for Monday's class or Tuesday's class, and we'll go through anything from units 4, 5, and 6 that you guys had questions on. You should have unit 7 learning guide printed for next day. I'll spend as much time as you guys want going through 4, 5, and 6, specifically 5 because we just finished it today. But anything you guys want to see in those units, I'll go through next day. But if nobody has questions, well, I just got to assume you know what's going on, and we're going to move on. So come prepared with questions on the chemistry stuff next day. If there aren't any questions, we're going on Unit 7. We got to just keep rolling. So there you go. Hopefully, I see you guys tomorrow at climbing at Nice Gym. We've never been to Nice Gym before. I've never been there before, but climbing is always fun. You don't have to be really particularly good at climbing things. There's instructors and whatnot there. That's tomorrow. If you wanted to go sailing, Connor's dad, your dad is associated with it somehow, right? Does he work there or volunteers there or something, Connor? The irony of us going to a gym associated with Connor's father, he's a coach there. There you go. I knew he was affiliated somehow. So there you go. Is he going to be there tomorrow, Connor? Do you know? Your arm's all, bandaged up. You can't even climb tomorrow. That's unfortunate. No, he won't be there. All right, so there's other coaches, so we'll be there. It's a new gym. They just built it like 2 years ago, I think, or something like that. So it's brand new. It's a really cool facility. I've seen it online, and it'd be good to see you guys there. If not, we'll catch you in class on Tuesday with questions from Units 4, 5, and 6, or moving on to Unit 7. And we're definitely in the home stretch here, guys, so just keep going and we'll be done before you know it. So thanks very much. We will see you guys on Tuesday. Thanks.